Hi all, welcome to part 21, module 2, computer networks. So we were discussing the CSMA protocol and we already seen the carrier sense multiple access protocol with the three variation, that is one persistent, P persistent and non-persistent CSMA in the previous lecture. Now we are going to see a variation of the CSMA protocol called the carrier sense multiple access with the collision detection. So far in the on persistent, P persistent or non-persistent, so all those variations, whenever there is collision, so after means this collision, what they will do after some point of time, maybe with lack of acknowledgement or in some other way, when they came to know about it, so in that way only we didn't deal with the collision, means particularly in our previous discussion. So whenever there is a collision, if the station is aware about the fact that its data get collided, then I can wait for some random amount of time, then I can try again. So like that only we already seen. Now we are going to see the collision detection part. So how that detection is to be done and what are all the things you have to be taken care for a proper collision detection. Okay. So the persistent and non-persistent CSMA protocols are definitely an improvement over the Aloha protocol, because the carrier sensing part is being introduced, right? So both are better to the Aloha, the pure as well as the slotted Aloha, because they ensure that no station begins to transmit while the channel is busy. So if the channel is busy, that sensing will be done properly and you will not send the data. So in that way both are better. But what about collision? So if two stations sense a channel to be idle, definitely both are going to send simultaneously, say, right? So and they begin transmitting simultaneously and their signals will still collide, right? So because both are attempting at the same time. Now so the key point is the simultaneous trying again. So another improvement is that for the stations to quickly detect the collision and abruptly stop transmitting. So if you are able to detect the collision quickly, in the sense, I mean, you have you can simply sit idle, let the collision be detected at some later point. So instead, if you have some extra mechanism by which the collision, if it is there, if you can quickly detect it and you can abruptly stop, then you could save some something, in the sense unwanted sending of further part of the message you can avoid, right? So that is the idea. So try to detect the collision quickly and abruptly stop transmitting rather than finishing. I mean, even though the data get collided, you continuously sending the data, but actually some part of the data collided, but you don't know about it. So instead, if you can detect the collision at some early stage and you can abruptly stop it, it will be better, right? Since they are anyway the data is irretrievably garbled, right? Some part is garbled, so without sending it with the further remaining part of the data, you can try to abruptly stop the communication. And this strategy of course saves time and bandwidth, because unwanted, I mean, even though the data get collided, the remaining part you are not going to send, right? So that can save the bandwidth and the time from your side. So this kind of protocol is what we call as the carrier sense multiple access with the collision detection, and is the basis of the IEEE 802.3 Ethernet local area network. So the collision detection is actually an analog process, in the sense the station's hardware must listen to the channel while it is transmitting. So if the signal it reads back is different from what is being sent by the channel, then it can detect the collision. So this is a trick, I mean, how the collision detection is happening, and that we are not going in detail, but we are trying to see an idea about it. Like, it's an analog process, it is something a hardware oriented process, signal related process. So from the software part you don't have to worry about it, but still the process is something like this. When you send some data, you know the type of signal, its strength, the encoding technique, everything, but you are sensing something different also at the same time. I mean, the collided signal with some different level of amplitude, and also by looking at that amplitude variation, maybe either the signal get added or subtracted, right? So from the normal voltage level that you are expecting, it will be something extra high or low. So that is the way you can detect the collision, and it is something happening at the hardware level. So the implications are that the received signal must not be tiny compared to the transmitted signal. So that is one problem we are facing with the collision detection. To make the collision detection happen, the collided signal, when it is received back, it should have some minimum voltage level, because if it is too tiny, too much attenuated, then the detection is actually impossible. So particularly when it comes to wireless network, the received signal is typically say this many, some 10 lakh times weaker than the transmitted signal. So it will be difficult for us to detect such a scenario, right, such a collision kind of things. And so that is why in wireless network, particularly that Wi-Fi and all, we are not using this collision detection variation of CSMA. Instead we are using another variation called the collision avoidance, right. So that looks better, right, CSMA with the collision avoidance. So that is something we are using in wireless network particularly, because where the collision detection part is slightly difficult. And also the modulation technique must be chosen to allow the collision to be detected. So that encoding modulation technique also has some role on collision detection. Now some terminology like contention transmission or ideal state. So in a typical CSMA bar CD network, any station will be if you look at the underlying media, if it's look at the timeline, you can see that at any time a particular frame will be successfully sent by the media, just like these 4 cases, or the contention period, in the sense the bandwidth of the media is simply wasted, in the sense for example here you can this particular station is sending its frame successfully, okay, so the transmission is going on nicely without any collision and all, and at T0 maybe this is station A is trying to send the data. So if you look at the time like this, maybe at 10 o'clock it started sending the data, at 10 maybe T0 is like some 10:30. So in between, say at 10:15, 2 stations, say B and C, were trying to send the data. What they will see, they will observe that the media is, they will sense and they will understand that the media is occupied. So what they will do, they will wait for the media to be free. Depends on whether you are using on persistent or non-persistent. In non-persistent, both will continuously wait. In non-persistent, that waiting is something random. So that is different. Anyway, we will assume that both will wait until the channel is free. So at 10:30, say this T0, both B and C are observing that the channel is free. So what they will do, the both will try sending their data simultaneously, assuming one persistent, okay. Otherwise other things you have to compromise, like longer delay and all. So simplest way we can use one persistent. So what they will do, both B and C are trying to send the data simultaneously, and definitely the data is going to be collided, and that will be detected, and the transition will be aborted. Again after some period of time, both are trying simultaneously, and this kind of, so all these things are actually collisions, and the signal is being collision is being detected and the transition is aborted. So that is why the smaller pieces of information you can see. So this is what we call as the contention period. Many stations are trying to access the channel at the same time, or contending for the access of the media, and they are getting collided, and it is simply wasting the media without no one is actually sending any information. But after some time, once contention slot is over, again we are getting a useful transmission, and again some contention slot. So like that the whole thing will proceed, and in between sometimes no station want to send the data, and that also possible, and that is what we call as the idle period. So at any time the CSMA over CD protocol, if you are using the media, will be in contention, transmission, or in idle state. So at point T0, just like the example I mentioned, a particular station has finished transmitting its frame, that is A. In the example, any other station having frame to send is now will try attempting sending at T0, for example B and C. And if 2 or more stations decide to transmit simultaneously like B and C, there will be a collision, of course. Now if the station detects collision, it will abort the transmission and wait random period of time, and then tries again. And therefore the model of CSMA over CD consists of alternating contention and transmission period. But we will if time allows, we will see the efficiency derivation, and that time it is not going like an infinite number of contention periods. So there is some kind of cycle you can observe, and with that we will see how the efficiency is there. So that is up to the efficiency part if we are reaching there. Otherwise you can see it simply that CSMA over CD, the model consists of alternating contention and transmission period with some idle period, just like this. And that means nobody want to send some data. condension transmission and idle periods occurring when all stations are idle period is when all stations are quiet, they don't have any work to do. Okay. Now the algorithm, contention algorithm on the generalized case is observed here. So we will see the worst case scenario in the sense, let the time for the signal to propagate between two farthest station be. So we are trying to see the contention algorithm. I mean, contention means the two or more stations simultaneously sending and collision is occurring and its detection is happening and the aborting of the transmission as early as possible. So all together to achieve it, what we have to take care. Yeah. So what we can see is, assume that two farthest station, for example, this is common media, this is A and this is B, situated very far, for example, within that particular land, to identify two farthest station, and what is the distance between these two farthest station, let it be some tau. One second, I am getting a call. Let's continue. So this is regarding the CSMA bar CD performance in a worst case scenario, the contention algorithm, how it is behaving. So what we can see is, we assumed like the time taken to for a signal to propagate between two farthest station to be some tau, so some value like this. So farthest in the sense, if two stations were like this is A, so this is a LAN, and suppose these two are at the farthest distance, and the time taken to transmit the signal between them be tau. So actually this is something, the propagation time, right? So when it comes to the time taken, the propagation time of the longest pair, something like that. So at T0, one station begins transmitting. So at some T0, if you look at the time diagram, at some time T0, on station start transmitting, say A starts transmitting the data. Okay. Now at the T0 plus tau, because for the transmitted signal to reach at B, it will take the time taken to transmit that particular frame we assumed to be tau, right, the propagation time. So at T0 I started transmitting, and at T0 plus tau time, the signal is supposed to reach the receiver, that is B. But just before that, okay, just before that, so this is T0, I started sending T0 plus sigma, it will reach here, but just before that, so just before, in the sense, we are just taking some small sigma value, say some sigma difference, that is T0 plus tau minus some sigma, and an instant just before the signal arrives the most distant station, that station also begins transmitting. So that is a scenario, because this B, when sends the medium, it found that the media is free, but actually A started sending before that, and its data is on the way. In between, B sensed some neighborhood of it, and it found the channel is free, and it started sending the data, and the transmission from B started at the time T0 plus tau minus sigma. So definitely the data that is coming from A, it is almost here, and now B also started sending, and the collision happening at this point. Okay, see now, of course it detects a collision almost instantly and stops. So provided we have a strong collision detection strategy, and but the little noise burst. So once the collision is there, some collision signal will be generated, right? So as part of the collision, some collision signal will be generated, and this little noise burst is coming back. And how long it will take for the collision signal to reach from the collision point back to A, then only I can understand that it is my data that being collided, right? So again, that same tau unit of time it will take, tau, actually tau minus sigma, approximately tau. So but the little noise to come back, the total time is like the forward direction, I started sending it to T0. Now after T0 tau minus sigma, the signal get collided, and for the collision signal to return back, it took another tau unit of time, or tau minus sigma, like that. Okay. Now together you can round it to some 2 tau minus sigma. So this is after this much time, then that means something like a 2 times propagation time with some small value some small constant subtracted, maybe this one or 2 sigma, like that. Yeah, after the but this is something you can ignore. You can round this value to be some 2 tau. So the situation is like when you start sending at this point, collision happen at this is A and this is B. Collision happen at some farthest point, and the distance between these two is tau. So the collision signal to come back another tau, rounded. Some sigma variation will be there that we are going to ignore. Okay. So this much time is needed for the collision to be detected, I mean by A. In the sense A is having the mechanism for collision detection, but the collision signal has to reach A, then only A can start detecting it, right? So that will happen after 2 tau, that much time only. But the thing is that till that time, I mean till that 2 tau of time, A should continue its frame transmission, because in between if A stopped transmitting its frame, in the sense the frame is of smaller length and A's transmission of that frame completed before this 2 into tau, that much time, even though the collision signal is coming back, how A will understand that it is its data that get collided? Is it clear? So it's a very important concept. The A should continue transmitting the frame. I mean the collision of this this frame is longer enough so that some parts of the frame get collided and the collision signal is coming back. When the collision signal is coming back, A should, whenever A identified this collision detection, and that time there should be some data for A to send, in the sense the frame transmission time of A should be greater than or equal to 2 times the propagation time, something like this. So this should hold for the collision detection to happen in general. So that is what it is being trying to convey by the textbook, but instead of that I just use the terminology from the textbook, like 2 tau, like that. Okay, so hope it is clear. So after this this much time, which is approximately 2 tau, the collision signal is coming back. So till that A should continue transmitting its data. So in the worst case, a station cannot be sure that it has ceased the channel until it has transmitted. So the transmission of that particular frame should continue for some 2 tau plus time, I mean more than 2 tau time. Then only when that collision signal is coming back, it can understand that it is my data get collided and the collision signal is like this, and this collision signal came and I am still sending the data, so definitely my data get collided. That will be understood by this sending station only if it hold this property. What is the property? The frame transmission time should be greater than or equal to 2 times propagation time. So this is the conclusion. So that transmission of that sender should continue beyond this 2 tau. So the CSMA per CD contention can be thought of as a slotted aloha. So why in the sense slotted aloha? Because slotted aloha, we are dividing the time in discrete slot, and frame transmission is something within a slot, right? So in that case, the frame transition should happen 2 tau plus time, like that. So at least the frame transmission time should be 2 tau. After that only you should send the next frame. So the frame transition time of every frame you can set to be 2 times the propagation time between the farthest station. So like that you can set this propagation time, I mean frame transmission time, and ultimately it will now generalize to a slotted aloha kind of thing. Okay, so that is how you can ensure that the detection happen properly in case of CSMA bar CD algorithm. Okay. So hope you get an idea. So this thing, anyway, from your textbook you will be getting Tannenbaum, it's explained till this, but I will be taking some other example from some other source, and I will try to convince you this one with some more example, maybe in the next part, if it is, because in GATE exam and all, people are just framing concept with problems with this concept. So this is something a very valid equation that is to be there in any CSMA bar CD protocol. To make this collision detection happen in the correct way, collision detection, and once I detect that there is collision, I should be convinced that it is my data that get collided. For that I am making my frame transition time greater than 2 times the propagation time between 2 farthest points. Okay, that is the idea. So I will take a more generalized example or some simple example so that this concept will be clear for you. Thanks for watching.